Okay, thank you very much for a kind presentation. For those who don't know me, I'm João Bettencourt. I'm a PhD student here. I have a background in engineering, and I'm being recycled into a physicist by Cristóbal and Emilio here. And I'm going to show you the work I've been doing on the subject of Lagrangian Coherent Structures. So, a small outline of my talk. Well, I'll start by introducing the concept of coherent structures, then the reasons why we think it's we should study them, then a tool that we use to study them, another tool, and then my talk is mainly dedicated to the oceanic setting, but I'll take a small detour to show you some work that we did when we were studying the concept of these three-dimensional ridges. And then finally I will show you the results that we've been obtaining for these last few months. Okay, so I'll start with the concept of coherent structures. You know that in fluid mechanics the concept of coherent structures has many different mathematical definitions. Then that usually means that we still don't know very much what we are talking about. So I've chose to bring this quite textual definition of a coherent structure being a feature of the flow field that lasts long enough to be observed. And I will try to show you what I mean with this figure, and later with an animation. So we are looking at this is the output of a numerical model of the regional ocean, and from the outputs of the velocity field we calculate a scalar measure that it's called the Q criterion. The definition is not really that important. What's important is that this criteria, it allows you to see in the flow the regions that are dominated by rotation, that we usually associate with eddies, and regions that are dominated by strain, which are these blue regions, negative. And so what I wanted to show you to illustrate the concept, luckily this will start a movie, is that some of these patterns are long-lived and we contract them for a considerable amount of time. But others, the smaller ones, are short-lived, and between the time they appear and disappear, it's impossible to track them coherently. And that is the definition of a coherent structure. There's something that lasts long enough so that you can track it and identify it. Okay. So that was a definition, and I've showed you in what we call the Eulerian perspective. In this perspective, we look at a fixed region or a fixed region of space, and we study it by looking at the fields and their evolution in this fixed region of space. That's what we call the Eulerian perspective. The Eulerian perspective, however, has some limitations, and they are mostly related to the fact that it does not follow the motion of the fluid material, because you are looking into a fixed space. However, the other perspective that we use to study fluid motion, which is the Lagrangian perspective. This perspective, yes, follows the motion, and it looks at the material properties of the flow, such as transport, particle trajectories, and deformation of the fluid material. And because of this, we think it's a more natural way of describing the transport and mixing of the fluid material, and also it can be studied using tools from the theory of dynamical systems, which I will show you in a few slides. But first, I would like to try to convince you of why it is important to look at coherent structures in the Lagrangian perspective. And the reason is that it is believed that these structures are important for biological process in the ocean. Of course, this is not the only reason, but since my work is devoted to biology and fluids, then I'm using it for this reason. I can show you here two satellite pictures of plankton blooms, one in Namibia, in the southwestern coast of Africa, and the other one in the Black Sea. They were taken by the MODIS instrument aboard the NASA satellite, which I don't know the name. But you can see here these extraordinary concentrations of plankton that appear in an otherwise empty ocean space here. And in this case, you can see here in the Black Sea that these high plankton concentrations, they almost fill the entire space. But the reason why we think...
Excuse me, what is north and south?
Yeah, sorry. So north is like that. And
okay.
the satellite was looking in the... It was twisted. So east, west, west, east, and south, north. And you can see that these plankton booms, they take these very convoluted shapes, and then I will show you that these shapes are very similar to the shapes that we obtain when we identify these Lagrangian coherent structures. But besides plankton, and since the plankton is related to a whole trophic chain of living organisms, we also believe that the Lagrangian coherent structures are important at higher trophic levels, including the top. So in the case of top predators, I can show you here the results of a very interesting and, in my opinion, important study that was partially done here by Cristobal and Emilio, that shows that these birds, these frigate birds that are top marine predators, they also follow Lagrangian coherent structures. Of course, between plankton and the top predators, there is a whole series of interconnected levels. So it's only natural to assume that being between these two levels, Lagrangian coherent structures also have an important role. Okay, so it's about the motivation. Now, another aspect, of course, I've shown you two-dimensional studies, but the ocean is a three-dimensional body of water, and so it is only natural that these two-dimensional studies are extended into the third dimension. This third dimension in the ocean has these characteristics that, due to rotation and stratification, the horizontal motions in the ocean are much larger than the vertical motions. So one could think that vertical motions are not that important. But it turns out that these vertical processes, they are important because they enable the exchange of properties of water along the water column. And as an example, they allow nutrients that usually reside in below, at deep in the ocean, they can be carried upwards into the euphotic zone. That's where the zone where the sunlight penetrates. And then the upward transport of nutrients can make these plankton booms appear, because plankton needs not only light but also nutrients. And we know that vertical transport is more intense in certain regions or in certain settings, such as coastal upwelling zones that you can see here marked more or less around the globe. These zones are zones of extremely high productivity and fisheries, so they are very important to humans. But also are other regions, like here in an eddy, and when an eddy interacts with the winds, we can also have intense vertical transport of material, in a way that the intensity of this vertical transport in these settings, it's much higher than the normal intensity that we say it's very low compared to horizontal motions. So this is the main reason why we think that you have to study also the third dimension. Okay, so, but now back to the question of how do we use dynamical systems to study this. Of course, we start from the position where we consider particle trajectories in a fluid field, just like the one I showed you from numerical models or other sources, and we consider each particle to be a dynamical system that is governed by this equation, where here we would have the velocity field of the numerical model or the other sources. And we know that certain trajectories exhibit singular properties, such as stable and unstable manifolds, that impact the behavior of other particles in their vicinity. And that way, these stable and unstable manifolds, they induce coherent motion of particles in their vicinity, and they also connect as separatrices that partition the phase space in dynamically distinct zones, meaning that fluid here will behave in a different way than fluid, for instance, on the other side. These two characteristics, they are related to the concept of coherence that I talked to you about earlier, and so we kind of adopt these stable and unstable manifolds as a definition of Lagrangian coherent structures, because we would expect that these Lagrangian coherent structures to act as barriers to transport and to influence the flow of particles and material deformation. And so we come to the conclusion that we can equate Lagrangian coherent structures with separatrices in time-dependent flows. So I'm going to show you an example of what I mean. This is an animation that Emilio has kindly allowed me to use. You can see that the two patches were of particles. So it's material, it's fluid material, it's not a scalar field that we're looking at fluid material. That these two particles, one remains inside this area, and it doesn't mix with the outside. And while, let me just restart the other one. And while the black material is stretched, and eventually it will be transported to most of the spaces. So here we see two different behaviors, Lagrangian behaviors, because we are talking about particles material. In that one, we can these structures, they hold material inside and prevent it from mixing. And on the other hand, but now it's already here, material is mixed and stirred and mixed quite intensively by these Lagrangian structures. So, how do we use dynamical systems theory to identify Lagrangian coherent structures? There are several tools. We use the finite-size Lyapunov exponent, which was developed by RL and Bofetta and their co-workers. It's a measure of the rate of growth of a finite separation between two limits. So you can think of two particles initially located nearby that evolve in the fluid field, and they reach finally, after some time, they reach this separation. And then we calculate the finite-size Lyapunov exponent by calculating the time it takes for them to reach this separation. And then we use this formula here. So you can see that when these two particles, they are placed near one of these stable and unstable manifolds, the rate of separation will be much higher if they were located on other places, and the finite-size Lyapunov exponent will be higher. And so, from this we conclude that high values of the finite-size Lyapunov exponent signal the presence of these hyperbolic structures in our flow field. Like I said, there are other tools, but the finite-size Lyapunov exponent has two characteristics that make it a very nice tool to use. First, it requires only trajectory information. We just need to calculate the distance between the particles, and like Ismael showed in his paper, it's very robust. So even if you don't have a completely smooth velocity field, if you have gaps, or if it have a coarse velocity field, you can interpolate it, for example, and it will still give you an approximate location of this structure. So it's very robust too. So what we did, we applied this method to the data that I showed you, the velocity field from the numerical model ROMS. We calculated the finite-size Lyapunov exponent in a region of the flow field. That is, this is the African coast. So this is the region where we calculated this finite-size Lyapunov exponent. We used the regular grid, so we could have a sort of an Eulerian map. This grid, the initial distance between the particles, we set it at 3 kilometers, and we used 100 kilometers for the final distance, which is a suitable final scales to study these mesoscale structures. We also did it in 3 dimensions, so we calculated in 30 vertical layers, and we tracked the particles for 6 months. And the finite size distribution, finite size Lyapunov exponent distribution, is this one that I show you here. You can see that the higher values, they concentrate along these lines, similar to that animation that I showed you before, and that these lines appear almost everywhere in the flow field, which means there is vigorous mixing in this flow field, so that material released in one of these places can be transported up to other faraway places because of the presence of these lines all over the domain. So we also used the fact that we had 3-dimensional fields to calculate the profile or the vertical profile of the average value of the FSLE. We found that it decreases with that, and that means that activity is getting weaker and weaker as we go deeper in the ocean. We found this curious maximum around 100 meters depth. We still don't know how to explain this, but we think it's related to perhaps current intensity that could be higher at this depth, but we're still not sure. And of course, this tells you that the characteristics of the flow field have an impact on the distribution of the finite size Lyapunov exponent. And going back to Eulerian versus Lagrangian, here now we can compare these 2 different ways of seeing coherent structures. This is again a plot of rotation and strain dominated regions. Here rotation is white, and it gets darker as the straining starts to dominate the motion. Here you can see that this light area here, it's an eddy, and when you compare this to the finite size Lyapunov exponent lines, the lines of high Lyapunov exponent, we see that these lines they kind of form barriers around the eddy. So in the Eulerian and Lagrangian methods, we reveal the same identity, the same coherent structure, but the difference is that we see it differently. In the Eulerian perspective, we see it as a patch of whichever Eulerian measure you're using, but on the Lagrangian perspective, we see it as the space enclosed by these high finite size Lyapunov exponent lines. Okay, so like I said, we want to go to 3D, and our 2D algorithm, it could be extended directly to 3 dimensions, and I will show you an example of that in a moment. But like I said, in the ocean, the vertical velocities are much smaller than the horizontal velocities. So this creates a problem, because when we calculate the dispersion of particles, and the horizontal, it can be tens or hundreds of kilometers, in the vertical you would almost reach tenths of meters. So that is a problem, because then the vertical dispersion won't count to the final distance. So we decided not to use the vertical distance between the particles, and we calculated the finite size Lyapunov exponents layer by layer, like I showed you, but we still let the particles evolve in a 3-dimensional fashion. And we did it because it can happen that small displacements in the vertical can take particles into zones where the horizontal dynamics is different, and then that can affect the final distance between them. And in the end, after calculating the finite-size Lyapunov exponent maps, we use this definition of Lagrangian coherent structures as the maxima of the finite-size Lyapunovan fields. Like
is this equivalent to calculate the three-dimensional Lyapunov exponent and projecting into D, or it is not?
Well, yes, because if you calculate the three-dimensional Lyapunov exponent, you'll have basically the same results as if you use just the horizontal distance. Because the distance here is dominated by dispersion on the horizontal. So. Okay, so we want to find the maxima of the finite-size Lyapunovan fields, Lyapunov exponent fields, because that's where we think that Lagrangian coherent structures are. But in 3 dimensions, the maxima of the Lyapunovan fields are hidden in the volume data. So we need to think how to identify them. And to do that, we use the concept of a ridge, which is a region that maximizes a scalar field in a normal direction to it. And I have here an example. If you look at this picture, you can see that the 2D field is just the height of this mountain in every point. And you see that if a person walks along this path, like this gentleman here, if he moves sideways, he will start to go down. So in the direction perpendicular to this path, the field attains a maximum. So that's what we say it's a ridge. And of course, we can see these two conditions here. There is a local extremum of the field at the ridge point, and also that the direction normal to the ridge is the direction of fastest descent. Just means that if he continues in this path, he may go up and down, but he won't go down as fast as if he steps sideways from the path. So this is the definition of a ridge. Of course, in 3 dimensions it's different. You need to have these mathematical conditions to extract them. Basically, we say that the gradient of the scalar field in the direction perpendicular to the ridge is 0, so that in that direction the ridge is a stationary point, and then you have to impose that the second derivative is negative, so that the stationary point is a maximum. So the extraction method, with some minor details, basically just marches to the grid where we have defined our finite-size Lyapunov exponent fields and extracts the points that obey to these conditions. So, like I said, I will take you on a small detour because because before we applied this to our oceanic finite-size Lyapunov exponent fields, we tried it on a canonical turbulent field just to see what we would get. So we used the turbulent channel flow. It's a very well studied turbulent flow. It develops between 2 parallel plates, and it's driven by a pressure gradient in this direction. It's 3D, so you would have here the wall normal, the streamwise direction, and then into the screen you have the spanwise direction. So the solution of the laminar channel flow is one of the few analytical solutions to the Navier-Stokes equation, and it's given by a laminar profile, a parabolic profile. But the effect of the turbulence, as you can see here, is that the net turbulence force, it acts to accelerate the flow near the wall and to delay the flow off the wall, so that the turbulent velocity profile has this shape. This is due to the fact that if you look at the velocity perturbations in the streamwise and the wall normal direction, the PDF will have this shape. So the probability of having an event like this that is pulling fluid away from the wall, it's higher and is equal to the probability of having a turbulent fluctuation that pushes fluid into the wall. And this is the reason why the turbulent effect is to accelerate the fluid here near the wall and to delay the fluid away from the wall. So with respect to coherent structures, because that's what we're looking, we have here the smoke screen visualization. You can see that these structures, they all appear like these large bulges of fluid that is being uplifted from the wall, and then you have these small vortices that we call hairpins. So we applied this, we made our simulations with this software, with a pseudo-spectral solver. It's available at channelflow.org. We use standard dimensions and standard discretization. And I'm going to show you the velocity field in a streamwise wall normal plane. So you can see here that this is just, I'm showing just the turbulent fluctuations. So they are positive here near the wall, and they are negative in the center. So they are here, they are delaying the flow, and here they are accelerating it. And you must also note that the regions with high streamwise velocity, they appear in packets. They're not continuous, they appear in packets. And this is an important thing to keep in mind. So next we calculated our finite-size Lyapunov exponent, and here we use a three-dimensional grid. You can see here that each grid point has 6 satellite particles, and we integrate the trajectories of these 6 particles for each grid point, and then when a particle, when the distance between one of these and the central particle is greater than this final distance, we calculate the Lyapunov exponent. If in the end of the integration time interval the distance is not greater than the final distance, we set it to 0. So this is what we obtained. This is also a streamwise wall normal plane. You can see that this feature that we see these structures with this, they have this inclined, they have this inclined slope. I'll show you better in my final animation. And you can see, we think that these structures, they are signaling the presence of these hairpin vortices, and you can see why, because this is the vortex, and it's you can see that the vortex is rotating like this, and it is expelling fluid away from the wall. The wall is here, it's expelling fluid away from the wall, but then you have fluid coming into the wall. So here you have a stagnation point, and this stagnation point has an hyperbolic character. You have one direction where the particles are drawn into the point, and you have another direction where the particles move away from the point. So this hyperbolic character, and I remind you that the finite-size Lyapunov exponent, it signals areas where this hyperbolic character is more pronounced. You see that this, so I conclude that these areas here, this slope, is exactly what we see signaling here on this slope. So this is signaling the presence of a hairpin vortex. So of course this field evolves with time, and you see all kind of phenomena, but the most predominant are these hairpin vortices. Note that they also appear in packs. Here is one pack, then there's nothing, and then another pack will start. Actually, this is periodic, so probably all is the same 2 or 3 packs. But we think that comparing to the Eulerian flow, we think that this the Lagrangian picture is pretty much correct in representing the same things, but with another way. Okay, so now we take these 3-dimensional finite-size Lyapunovan fields and we extract the ridges. Ridges of 3-dimensional fields are surfaces, and you can see, I'm sorry the colors perhaps don't see very well, let me explain. The flow is along this direction, the wall is here, you have here the wall normal direction, and in the end you are seeing a spanwise plane. you can see that so I've only plotted the strongest structures, because if I plot everything it would be very hard to understand. It's hard already with just these surfaces, but you can see that the surfaces stands exactly at the separation between a region where you have a lot of high finite-size Lyapunov exponent organized as lines, and the region where it's almost completely devoid of finite-size Lyapunov exponent. This means that this region, it's not very turbulent. The turbulent intensity of this region is very small compared with this one, and that actually one of the things that you know, that in these turbulent channel flows, the region in the center of the channel is the turbulent intensity is very low, and it increases as we reach as we move towards the wall. But also, we know that sometimes this low turbulence fluid can actually reach the wall, and on the other hand, high turbulent fluid near the wall can almost reach the center of the channel. And that's what we see here, and we see that this surface is separating, is creating a barrier between the high turbulent fluid and the low turbulence fluid. And you can see here, so this is one time, this is the subsequent time, and another time. We see it's very complex, and they interact very strongly. You see, they are changing in this way, but they are also moving this way. And you can see that here you start to form a pocket of low turbulence fluid near the wall, while you have high turbulent fluid moving always almost near the center of the channel. And on this last slide, you can see that these two structures, they hit each other, but attention that they do not mix. If you look closely, I think you won't be able to from there, but if you look closely, you see that you can see here the clear separation between these two. So these structures, they control the movement of fluid in the turbulent channel, and they prevent fluid from mixing each other. So this is what we say when we say that this is what we mean to say when we say that structures, they act as almost material surfaces. Okay, so we were quite satisfied with these results, with this application of this method to extract the ridges. Of course, when we finished this, we had more questions than when we started, so this is work that will continue, I'm sure. But now, let me take you back to the FSLE fields. This is a repetition just to bring you down to earth. So now we applied the same method to this oceanic FSLE field. We have rather different results. I'm showing here, just to remind you the parameters of the flow. I'm showing here the surfaces that we extracted in the previous example by the same method, just now in this oceanic setting. You can see that they have this vertical shape, and they are this is the finite-size Lyapunovan fields in two layers. You can see that the structures, I hope you can at least, that these structures, they coincide with the maxima, with the lines of maximum Lyapunov exponent fields. If you look closely, you will see that we are using the same threshold of extraction, meaning that structures with an intensity lower than this threshold won't be extracted, and you can see that the structures generally get smaller and smaller as we go deeper, and that means that the intensity of the structures is getting lower and lower, just like the finite-size Lyapunov exponent fields that I showed you a few slides ago. And of course, we want to explain why are these vertical, and the reason is that since the dispersion is mainly horizontal, and these structures are supposed to be normal to the direction of maximal dispersion, since this direction is horizontal, then these surfaces have to be necessarily vertical. So in this picture, it's just the same, but here you have the the stable, the unstable structures, and here you have the unstable together with the stable structures, meaning blue unstable, green stable, and you can see that they practically follow this complex pattern of the finite-size Lyapunov exponent fields. So now returning to comparing Eulerian versus Lagrangian measures, but in 3D. We use the same eddy that I showed you before in the 2D plane, but now we have a 3D view of the field of the eddy. Let me say this red cylindrical surface is the Q criteria. It's the Eulerian measure. Okay, it's the Eulerian measure, meaning that this region inside the red surface is dominated by rotation. So it signals our eddy.
What's an eddy? What's an eddy?
An eddy. It's just
Vortex.
Yeah, vortex. Yeah, vortex. So it's the fluid here is rotating. And we can see that our Lagrangian structures, they also signal more or less the same location for this eddy, because they appear surrounding this Eulerian surface. But like I said in the beginning, when you look at material transport, you can see that the Eulerian criteria, it really doesn't tell you much, because what we did was that we seeded the inside of the eddy with the particles, and then we evolved calculated the trajectories, and you can see that these black dots are particles. They are leaving the eddy, they are crossing the red surface. So in terms of material transport, it's just as this surface wasn't there. And that is one reason why to study to study a phenomenon related to material transport in fluid flows, the Eulerian perspective is not the best, because it's in terms of material transport, it just doesn't relate at all. On the other hand, the Lagrangian perspective, you can see that the particles are following one of the Lagrangian structures, this unstable structure here. It might appear that they are also crossing this table, but they are not. I'll show you in 2 slides that they are not. So we come to the conclusion that coincides with our starting point, that in terms of material transport, Lagrangian structures do have something to say. Okay, so now I always have to feel that I should apologize for the figure, because it's almost unintelligible. But this is the time evolution of those surfaces. So this is, I won't waste my time on this one. I'll ask you to pay attention to this one here, this is the top view of these structures. Just wanted to say 2 things. First, they are not completely vertical. You can see if they were completely vertical, you would just see lines. You can see that they have a small inclination in relation to the vertical. That is due, we think, to the different intensity of the mixing and the physical processes in each layer. And secondly, here we have our sets of particles released in different depths. You can see that more or less so this is like 30 days, so this is 4 snapshots taken during a 30-day interval. You can see that the particles, they rotate. Most of the particles remain inside. They are forced to remain inside by these Lagrangian structures. However, you can see that filamentation event that I showed you on the previous slide. And you can see that the material is leaving the eddy along the unstable structures, and also here it's kind of returning, following the stable. So you can see that these structures, they really show you the pathways through which material flows in a fluid. So why does it seem that the particles are crossing? If you look here at day 7, you see that here is an empty space between these 2 structures. So let me just say that the resolution of our study is not very big. So what we see as an empty space is actually it's a kind of an entanglement of stable and unstable manifolds, and there are other processes that are working so that in the end, at this resolution, we see this effect. Mainly, I really don't remember now the name of the process, but it's well documented. But with the results, what happened is that the particles, some of the particles, they leave the eddy through this empty space. You can see that there is a part of the particles that are on the other side of this surface. And you can see clearly here that the filament is formed by two sets of particles. The original set of particles that remains rotating inside the eddy, and the set of particles that left the eddy along this path, you can see here, and they form the part of the filament that is flowing outside of the eddy. So actually, the particles, they do not cross the stable manifold. They leave the eddy and then they flow along the unstable manifold like those inside the eddy. And so finally, we wanted to quantify this filamentation. So what we did, we tracked the eddy. We tracked the eddy for 30 days. This is the trajectory of the eddy center. And at each day, we calculated the percentage of particles that left a radius of diameter of 200 kilometers centered on the eddy center. And you can see that filamentation is higher at 100 meters depth, and it decreases as we move to deeper depths. So the maximum of filamentation occurs at 100 meters, which coincides with that maximum that we saw on the average, on the profile of the average finite-size Lyapunov exponent fields. We think these are related, but we are still working on an explanation for it. And basically, this is what I wanted to show you, some conclusions. So like I showed you, the Lagrangian view can highlight aspects of material transport that are missed by traditional Eulerian tools. We can use the tools from dynamical systems theory to study Lagrangian coherent structures. At the mesoscale, they populate the ocean, giving rise to strong mixing. In 3 dimensions, actually the main objective of our work was to see what happened in 3 dimensions, and we see they show up at quasi-vertical structures because horizontal dispersion dominates. Actually, in the channel flow, they weren't vertical. They didn't have a preferential orientation because dispersion had equal intensity in all the 3 directions. So these were actually 3-dimensional. And finally, they control material transport in and out of this mesoscale eddy. And like I showed you, also they control the position of the turbulent non-turbulent interface in the channel flow. So future work, what happens at the submesoscale or in regions of enhanced vertical transport? We are very interested in this. What is the effect on the gradient of scalar tracers released in the fluid? And also our main objective to study, to learn about the impact of these structures on biogeochemical processes in the ocean. And finally, just to say, this is the image of another plankton bloom, and you can see that here, this is the plankton concentrations. They almost perfectly track the limits of the eddy, and also on this situation. And this is a picture from the Envisat satellite, the MARIS instrument. And that is all. Thank you very much.
Thank you, João. No questions? Students first.
I don't know where to begin. First, maybe experimental. These particles that you traced over time, what kind of particles were those?
Passive.
Passive particles, but they were dropped there, or they were naturally? Were they actually the plankton particles that were already there, so measured by bioluminescence or something, or?
In the satellite pictures.
In the satellite pictures, yes, that was plankton, right? But
Yeah.
I mean, you mentioned another experiment. That was, how did you measure these particles at a certain depths?
Oh, it's a numerical model. It's a numerical model of the ocean.
Okay. Right.
Yeah.
So all plots shown with depth resolution were numerical models.
Yeah. Numerical models. Yeah. So all calculations were made with numerical models.
More questions?
I wasn't too sure about the interdependence of the Lagrangian structures and the eddies. Are they somehow self-sustaining or causing each other? I mean, the sustainability of those, do they support each other somehow? I mean, you need apparently the eddies to have these Lagrangian structures, but you also need the Lagrangian structures to protect the eddies, right?
Yes. let me start. That's a difficult question to answer. So, an eddy is a feature of the Eulerian in this case numerical methods. It's a feature of the equations that you're solving. So, the fact that the eddy exists, it's related to several processes like the forcing. I mean, if you remove the forcing, the eddy will disappear. Also, the regime that you're using, that is what governs the dynamics of the eddy. But the question is that if you put material inside the eddy, and if you look at the way that the material is evolves, then that evolution is controlled by the Lagrangian structures that surround the eddy. Was that? So the fact that they exist surrounding the eddy is, let's say, it's a mathematical result. Okay. So if you have an eddy under these circumstances, you will surely have Lagrangian structures around it. And actually, you can think, for instance, that there are some eddies in the ocean. They can carry water inside of them for months, perhaps even years, and the fact that they are impermeable to the exit of material is a consequence of this Lagrangian structure existing around them. So I say I really can't answer because these are two different ways of observing the same process. So saying which one causes the other, it's
I think I get it.
yeah, it's difficult.
More questions from students? And if not, again?
Well, I would say that comment on this is the same thing. So I mean, it's just two views of the same thing.
Yeah.
So in the ocean you have one thing.
Yeah.
Where they use Eulerian or Lagrangian description, it's the same thing you are saying. So, not two things. And also, you talk about coherent structures. Then we work a lot with coherent structures. Then we usually take another viewpoint. Coherent structure is something that has as an entity in itself. So it's a big thing. Then you ever studied? So let's say that the properties as a whole. So let's say the Lyapunov exponents or the stability of these objects and these things. Don't you ever track that? That may be useful. Understand what I mean? For instance, how long does an eddy live? So is it stable perturbation?
Yeah, I see. Well, actually, that is the. So this work was mainly to learn how can we extract these features, how can we know where they are, how can we detect them. But yes, I mean the interesting work is exactly to study their evolution. How do they appear? How long do they live? And why do they disappear? Because of course they don't live forever; and they disappear. So, but we're not really there yet.
More questions or comments?
This filaments, as you explained, is there a way to decrease the size of the eddy, or is the particles that escape from the eddy are substituted by new particles from
Yeah. Let me to press the button, but So what you see here is basically is an eddy, and these eddies, you can see that they interact. They form. You can see that they are forming filaments in the Eulerian sense. So actually, this they're not static. They have a history of close encounters, of mergers, and that's how that's how they exchange properties with each other, and how they change size. Eddies can merge and become bigger, and they can two eddies can destroy each other, and yeah. But of course, most of the work is done by looking at Eulerian variables. This Lagrangian perspective in terms of coherent structures is just it's a recent field. So we are still working towards answering those kind of questions in terms of Lagrangian structures.
Daniel?
There's this huge structure in the Pacific which they call sometimes the washing machine or something, where all or a lot of dirt and everything is being trapped over years, and it spends like, I don't know, 30% of the Pacific area. Did you apply the methods to this and see if you could see filamentation surrounding one area, or would that not apply?
To say yes, I know that that particular, it's called the Pacific Island of Garbage, or
yeah,
yeah, because it's actually it's plastic garbage. Well, I have to say that.
Let me start the other way. Here you have many, let's say, semi-sized clusters or eddies. Would you see a similar structure if you go much bigger?
That's another interesting question. Because in the ocean you have several scales of motion. So you have the micro scale up to basin scale, like with the width of an ocean. This work is done at the mesoscale, and the mesoscale is one of the most. It's the most in terms of turbulence, it's the most energetic scale of motion in the ocean. And at these scales, we have this kind of behavior, and this behavior is and let's say the characteristics of the motion at this mesoscale, it's favorable to the appearance of these Lagrangian coherent structures.
So basically you have a relation between feature size and velocity distribution, I guess.
Exactly.
The velocity distribution is not going to change, and if you now go on a much bigger scale.
Yeah, the change, and I can show you that. I have to close this, and I can show you that. And I can show you that, for instance, with the finite-size Lyapunov exponent field, we can track these structures, this kind of hyperbolic structures, very well. And these kind of hyperbolic structures, they are very abundant at the mesoscale, and you can see why. You can see that here, right where they cross, this hyperbolic point where you have an unstable and unstable manifold, you have an area of high strain, and that is due to the interaction of both of these eddies. So in the mesoscale, you have a lot of these eddies interacting each other, and they create this kind of hyperbolic structures that, if they live long enough, we can identify with Lagrangian methods. But at the sizes of those islands, it's another scale, and I'm really not sure what we will see in those kind of scales.
And related to this, the Coriolis force at this scale is relevant or not?
Yeah. Yes.
It is. But it's not in the model.
Yes. It is in the model.
Okay.
It's what makes the ocean essentially two-dimensional. It's important. Until above the kilometer scale is one of the most relevant forces in the ocean.
And also
they are like this because of Coriolis.
So they are more counterclockwise and clockwise.
And they have properties.
Yeah, the motion of the eddies is determined by the characteristics, but also by the variation of the Coriolis force. So it is important at this class. And of course, one of the ideas that we are now trying to do is to relate the motion of the eddies with the motion of these Lagrangian coherent structures.
Last question, Thomas?
What are the boundary conditions of your simulations? I mean, you did not simulate the whole Earth, or did you?
No, actually, I didn't simulate anything. This simulation was the data was given to me, but basically, so this is. Let me go back to the full domain. So this is the full domain of the simulation. This area is nested into another simulation with a bigger area and smaller resolution, and that simulation, the boundary conditions, basically they are derived from climatology, average fields, and on one hand, and also by simulations of even higher scale of the whole ocean at higher resolution. So it's all nested into each other. And so the inflow and outflow boundary, it's determined by this global circulation models that they use.
Okay, anything else? If not, thank you.
Thank you.